Okay, so please be reminded that your due date for project 1 is this Friday, okay? Before 12 p.m. 12 a.m. Okay, so today we are going to learn about analyzing the stability of system, okay? Of control system. And the first thing, the first method, okay, to analyze the stability of a system is called Routh Hurwitz Criteria. Okay, so let's look at this chapter and what is Routh Hurwitz Criteria. Okay, so after completing this lecture, you guys will be able to determine the system stability using Routh Hurwitz Criteria for normal cases and special cases. So there are two types of cases, normal and special cases. And for today, inshallah, we will cover only for normal cases. Okay, so before we go into learning about Routh Hurwitz criteria, let's refresh a bit about system stability. I think you have learned this just before midterm break last week. Okay, so a natural response definition. The system is stable if the natural response approaches zero as time approaches infinity. So if you look at the first figure here, so if your graph or your time response reaches a constant value, or in this case, for natural response, it will reach a value zero at time approaches infinity, then the system is stable. So the other two figures, the middle figure here, the system is unstable because the time response or the natural response is going away from zero. While the third one, it's marginally stable because it keeps oscillate. Okay, the natural response keeps oscillate about the value zero, but never actually reach the value zero. So there are three types of stability. We have stable system, unstable system, and marginally stable system. So a system is unstable if the natural response approaches infinity. And a system is marginally stable if the natural response neither decays or grows, but remains constant or oscillates about the value zero here. Okay, so there are three types of stability, and these three types are important from here onwards, okay? Okay, so let's look at an example of stable system. So let's say you are given this block diagram that has a transfer function 3 divided by s times s plus 1 times s plus 2. And it's a unity feedback. So you can find the closed loop poles. So find the closed loop transfer function and then find the poles, okay? Then you can plot the poles on S-plane. And after you plot the poles on S-plane, then you can determine the time response and plot the time response. If you look at the time response here, it is actually similar to case number 1, stable, because it reached a constant state or steady state value equals 1. Okay, so as the time approaches infinity, the natural response approaches zero. Okay, it is shown by the graph CT here. And if you look at the poles plot here, all of the poles of the closed loop system or closed loop transfer function are on the left-hand side of S-plane. Okay? It is on left-hand side or negative values. So we can conclude that stable system have poles only in the left half planes. So if your poles of closed loop system or closed loop transfer function are all on the left-hand side of S-plane, then the system is stable. Let's look at an unstable system. So you have another block diagram with transfer function 7 divided by s times s plus 1 times s plus 2. And it's also a unity feedback. Then you can find the closed loop transfer function and find the poles. And you can plot them on S-plane. Then you can also find the time response and sketch or plot. So here, the time response is increasing, okay? Becomes bigger and bigger as the time approaches infinity. So as the time approaches infinity, the natural response approaches infinity as well. So we can conclude that for unstable system, if one of the poles, so at least one of the pole is on the right half plane, like in this figure here, we have two poles actually on right hand side of S plane, then the system is unstable. So stable system, all of the poles will be on left hand side of the S plane, while for unstable system, at least one of the pole in the right hand side, then the system is unstable. Okay, so let's summarize the system stability based on poles location. Okay, so stable system will have poles located on left hand side. Okay, so if your system or transfer function has all the poles on left hand side, then the system is stable. Meanwhile, if one of your poles is located on right hand side, then the system is unstable. And the third one is when you have poles located on the JW axis or J omega axis here, then the system is marginally stable. Okay, so please remember where the location of poles and what is the system stability, okay? Because this one will we will use this concept later on, okay, in subsequent lectures. Okay, now let's look at Routh Hurwitz stability criteria. So it is a method to determine the number of closed loop system poles that are located in the left half plane, right half plane, or on the imaginary axis. So it's a method to determine how many poles that are located on left hand side, right hand side of the S plane, and also on the imaginary axis. So you can actually determine the poles by finding it straight away from the transfer function. But sometimes your transfer function can be complicated, okay? Can have a lot of terms, maybe until s power of 7, for example. So if you have s power of 7, it's difficult to factorize. So to ease the process of finding the poles, then we can use Routh Hurwitz stability criteria. Okay, so there are two steps. The first step is to generate the Routh table. And then second step is we interpret the table that we generated, okay? So let's look at this method, how to do this, okay? Okay, so let's say you have a transfer function, open loop system, ns divided by a4 s power 4 plus a3 s power of 3 plus a2 s power of 2 plus a1s plus a0. Okay, so to generate the table, the first thing that you need to do is you need to determine the highest power of s of the denominator. Okay, so here the highest power is s power 4. So your table will start with s power 4 because that is the highest order or the highest power of denominator. So you start your table with s4, followed by s3, s2, s1, and s0. And then we fill the two top rows, which is row S4 and row S3, alternatingly with coefficients of the denominator. So here we have A4, so we put A4 here. And then A3, we put below A4. And then A2, and then A1 below, and then A0. And then we don't have any more coefficient, then we just put 0 for the remaining spaces on the table. So we fill the two top rows first, alternatingly with the coefficient of the denominator. And then we want to find the remaining rows, S2, S1, and S0. So we just follow this formula. Okay. So this formula is actually, you don't need to memorize each of the spaces. Okay, there's a pattern, pattern in this formula. So I don't know how you want to memorize it, but the way I memorize it is that negative determinant of, look at the two top rows, so A4, A3, and then the next column, A2, A1, divided by the value of the row above, A3. And then the next column, negative determinant of A4, A3, and the next column, A0, 0, divided by the value of row above, okay, which is A3. Okay, same for the last one here. So negative A4, A3, and the next column. So next column, there is nothing, okay, no next column. So we just put 0, divided by A3. And then we repeat the process for row S1. So for row S1, you just look at the two top rows, which is A3, B1, A1, B2, divided by the value of the row above, B1. Okay, so you repeat the process. Okay, same pattern. Okay, so I don't know how you can, how you want to memorize it. Kena buat exercise lah, nanti boleh memorize. Okay, so we fill the next rows by calculating the determinants. Okay, so ni determinant. Okay, so you just fill the empty rows by calculating the determinants. Okay, so that's the method to generate the Routh table. So now let's interpret the Routh table. So the number of roots of the polynomial or of the denominator that are located in the right half plane is equal to the number of sign changes in the first column. Okay, so we will look at this later with example. And if there are at least sign changes, at least one sign changes in the first column, then the system is unstable. Okay, so I think it's good if I can show you an example rather than Babel. Okay. Okay, so let's look at this example. So you have a unity feedback system. So the forward transfer function is 1000 divided by s plus 2 times s plus 3 times s plus 5. Okay, so the first thing that you need to do is you need to simplify the block diagram. Okay, you need to find the closed loop transfer function or the final transfer function. So first, simplify the block diagram. So this is a feedback loop. So you need to use a feedback formula. Okay, so GS divided by 1 plus, because this is minus, so this becomes plus, times plus G times H. Okay, so here G is the block here, and H is simply a line, okay, equals 1. Okay, so if you use the formula, you get C over R equals 1000 divided by S plus 2 times S plus 3 times S plus 5 plus 1000, okay. Then you can simplify the denominator first so that you can use it, use the coefficient in the route table. And then this is the closed loop transfer function. So you want to generate the route table. So the highest power is power of 3. So you start your table with s power of 3, followed by s power of 2, s power of 1, s power of 0. And then you fill the first two rows, which is row S3 and S2, with the coefficient of the denominator. So here 1, so you put 1 here. 10, so you put 10. So ignore the slash here first. So 10. And then 31. And then 1030. Okay, so you don't need to put the last column, okay, because there are no more coefficient. But this example, you just put the 0 for nothing lah, okay, untuk tak ada apa-apa. And then you can simplify the rows that has similar factors, okay. So macam second row ni, in the second row, you have similar factors of 10, okay. So you can factorize 10, so it becomes 1 and 103. But you can also not factorize, okay, it will produce the same result. So if you are unsure, then just leave it as 10 and 1030. You don't need to factorize. And then you calculate the row S1. So the formula is negative. So you look at the two top rows, the two rows above. So 1, 1, 31, and 103 divided by the row above 1. And same with the second column, negative 1, 1, 0, and 0, okay? Divided by 1. And then we repeat for row S0. So row S0, negative 1, negative 72, 103, and 0, divided by negative 72. And the second column, it's negative 1, negative 72, 0, and 0, divided by negative 72. Okay, so that's how you determine the, or that's how you generate the route table, okay? Okay, so if you look at the first column, so to determine the system stability and determine the number of poles that are located on right-hand side of S-plane, so you need to look at the first column. Okay, so on the first column, from row S3 to row S2, there is no sign changes, meaning that positive 1 to positive 1. Okay, so it's positive, no sign changes. And then from row S2 to row S1, it changes from positive 1 to negative 72. So there is one sign changes here. So one sign change here. And then from row S1 to row S0, we have another sign change from negative 72 to positive 103. So one sign change here. So there are two sign changes. So two sign changes in the first column, meaning that there are two poles located on right-hand side of S-plane. And when there's a poles on right-hand side on S-plane, then the system is unstable. Okay, so that's how you generate the route table and analyze the route table. Okay, so any question before we proceed? Yep.
Sir, macam mana yang 10 tu dia jadi 1 dengan 1030 tu jadi 103?
So dia factorizekan 10 sebab sama faktor dia, factor dia 10. Tapi tak payah factorize pun tak apa. Dia factorize kan sebab dia rasa lagi senang, tapi kalau saya tak factorize kan sebab nanti jawapan yang lain pun akan sama je dengan factorize dan tak factorize. Okay, so actually I want to show tutorial terus. Okay, so let's do tutorial number 8. Okay, so let's do tutorial number 8. Okay, so we do tutorial 8, number 1A, okay? So determine the stability of the following systems using suitable Routh Hurwitz criteria, assuming the system as an open loop with a transfer function GS. Okay, so the question specifically says that the system is open loop, okay? So open loop maksudnya dia tak ada feedback, okay? Tak ada feedback. Okay, so dia tak ada feedback and open loop with the transfer function GS. So you don't need to simplify any block diagram, okay? So transfer function GS is given by so GS equals 1000 divided by S squared plus S power 4 plus 2S cubed plus 3S squared plus 4S plus 5. Okay. All right. So the first step that you need to do is to generate the Routh table, you need to look for the denominator only. Okay. Okay. So denominator ds equals s power 4 plus 2s cubed plus 3s squared plus 4s plus 5. Okay, so here your denominator has highest power equals 4. So we start our table with s power of 4. So s power of 4, then s power of 3, okay. So s power of 4, s power of 2, s power of 3, power of 2, and so on. So let's fill the two top rows with the coefficient of the denominator. So here coefficient is 1, okay. So we have 1, so 2, and then 3, 4, and then 5. Okay, so we have finished or runs out with the coefficient. So the remaining block on the two top rows, we can put 0, okay? Sebab tak ada coefficient. Then we can find row S2 using the determinant. So negative determinant 1, 2, 3, and 4 divided by 2. Okay. Dua row yang atas divided by row atas dia. So here we get 4 tolak 6, negatif 2, dapat 1. Okay. Nanti check lah betul tak. Okay, and then the next column, it's negative 1, 2, 5, 0 divided by 2. So we get 10, 5, 5. Okay, the last column, it's negative 1, 2. And the next column is empty, so we put 0 divided by 2. So we get 0. Okay, then we fill the row S1. Okay, so row S1, negative determinant of 2, 1, 4, and 5 divided by 1. So you get 10 tolak 4, 6. Negative 6. And then the next column, 2, 1, 0, 0 divided by 1. So you get 0. So you get 0. Okay, the third column also 0. Okay, tak perlu kira, nak kira pun boleh. And then lastly, row S0. Okay, row S0, negative determinant 1, negative 6, 5, 0 divided by negative 6. So you get 5. Okay. And then the remaining column, 0 ni nanti kira sendiri, betul tak? Okay, so now you get your Routh table. Then the next step is based on question, determine the system stability. So determine the system stability from the Routh table. So we need to interpret. So to interpret, we look at the first column and look for any sign changes. Okay. So from row S4 to S3, no sign changes, because positive to positive. And then from row S3 to S2, also no sign changes, because positive to positive. And then from row S2 to S1, so we have positive here and negative here. So we have sign changes here. And then from row S1 to S0, so again we have sign changes from negative 6 to positive. Okay. So here we have two sign changes. On first column. So when you have two sign changes, meaning that there are two poles located on right hand side of S plane. So when you have poles on right hand side of S-plane, meaning that the system is unstable. Okay, senang je, macam tu je. Okay, any question?
So, kalau row S3 tu dua part tu dia boleh factorize kan?
Boleh, tapi macam saya tak suka factorize lah sebab dia confusing kan nanti.
Oh, okay.
So that's why I said if you feel confident, factorize. If you feel macam unsure, it's better to not factorize because in the end you will get the same values. 1 here. Okay, so that's basically how you want to use Routh Hurwitz table and also interpret the table to determine the system stability. So let's continue with our lecture. Okay, so we continue with example number 2. So another use of Routh Hurwitz criteria is to determine a suitable range of gain. So usually your transfer function will have a gain k or a pamala or variable k or a variable k that when you change the value of k, then the system stability will also change at the same time. So this is important in later chapters or later lectures because we will see on how we change the value of k, how it affects the system stability. So the purpose of Routh Hurwitz criteria is to determine the range of k for a system to be stable or not stable. Okay, so let's say you have a transfer function Ts equals k divided by s cubed plus 18s squared plus 77s plus k. Okay, so you want to determine the range of k for stable system. So first thing that you need to do is you generate the Routh table. Okay, so start with s power of 3 because the highest power is s power of 3, and then followed by s2, s1, and s0. And then fill the two top rows. So 1, 18, 77, and k. And then determine row S1 using the determinant formula. Okay, so the determinant is negative 1, 18, 77, k divided by 18. Okay. So you calculate, you get 1386 minus k divided by 18. And the next column, tak perlu kira, okay? Dia kosong. Tapi if you kira, you get kosong, okay? You get 0. Not 0 marks, you get the value 0, okay? And then the last row, S0, use the same formula, the determinant. So determinant 18. Okay, so let's say this is A, K and 0 divided by A. So you get K. Okay. So usually, for me, when I see the determinant in this form, 18 Ka and then 0 at the very last place here, I will take this value K here as the final value. Okay, so tak payah kira, tak payah tulis pun tak apalah. Okay, mungkin ada orang dia nak tulis. It's up to you as long as you understand why its value, the value is K. Okay. Okay, then we determine the range of K from the Routh table. Okay, so for stable system, the rules is that the first column must have no sign changes. Okay, so when there's a sign changes in the first column, then the system is unstable. Okay, so to make sure the system is stable, then you must find the value of K such that there is no sign changes in the first column. So first we look at the row number 3. which is row S1 here. So 1386 minus k over 18 must be positive, okay? So it cannot be negative, because if this is negative, then there's a sign changes from S2 to S1. Because S2 is already 18 positive, so S1 must be positive. So this is must be greater than 0. Lepas tu susun dapat K less than 1386. And you need to look at the last row, row S0. So K here must also be positive, because if this is negative, then there's a sign changes from S1 to S0. Then the system is not stable. So K must be positive. So K bigger than 0. Then you combine the range. So the range of K for stable system is between 0 until 1386. Okay, so that's how you determine the range of K from Routh table. Okay, so let's look at one more tutorial before we end this lecture. Okay, so determine the range of K for the following system to be stable. Okay, so we look at the first, for this week, we look at the first figure first, okay? The first block. Okay, so the first block here, it's in unity feedback. So what you need to do is you need to simplify the block first. Okay, so you can use the trans function in the gray box here. So you need to simplify the block diagram first. Okay, so find CS over RS. So you will get K divided by S times S squared plus 4S plus 20 plus K. Okay, so you can do this later and verify whether this is correct or not. Okay, and then you simplify or expand the denominator so that we can use it in to generate the Routh table. Okay, so we expand. Okay, so S power 4 plus 4S cubed plus 20S squared plus S cubed plus 4S squared plus 20S plus K. Misalnya ambil soalan susah. And then simplify. So we get S power 4 plus 5S cubed plus 24S squared plus 20S plus K. Okay, so you get your denominator in expanded form. Then you can generate the table. So we start with S4 because the highest power is S power 4, and then followed by S power of 3. And then we fill the two top rows alternatingly with the coefficient of denominator. So we put 1, 5, 24, 20, and K. Okay. So we don't have any more coefficients, so we just put 0 here. And then we calculate for row S2. So for row S2, so determinant negative, determinant of 1, 5, 24, 20 divided by 5. So you get 20 minus 120, 100. So you get 5. That divided by 5, you get 20. You have to check, okay, betul tak? And then the second column, you get K. Okay, sebab ada 0 sini. So you just take the top value K. Okay, yang tahu je tahu. And then 0 here. And then row S1. So you get negative 5, 20, 20K divided by 20. So you get 400K minus 400 minus 5K of 20. And then this is 0. And then the last row. So you get K and 0. Okay. Then we can analyze, we can determine the range based on the fact that the first column must be positive so that the system is stable. Okay. So this is positive and this is positive. So we have this row. So here we have K in terms of K. So this value here must be positive. So 400 minus 5K over 20 must be positive. Okay, bigger than 0. Okay, susun. So you get K less than 80. Okay. And then the last row. So K here must also be positive. So K also bigger than 0. Now you combine the two range together. So tulislah conclusion sikit for a stable system. So K must be from 0 until 80. Okay. Okay. That's it. Any question before we end this lecture? Yep.
Yang 400 tolak 5K bagi dengan 20 tu memang kita kena buat larger than 0
Sebab yang ni mesti kena positif. Setiap ni mesti kena positif supaya sistem tu stable.
Yang K larger than 0 tu maksudnya apa sir? Yang bawah 80.
Ni row S0 ni. Row S0 kan ada K. So K ni mesti positif. Okay, so the first value here is from row S1. And second one here from row S0. Okay. I think in exercise yang tutorial yang second figure ni, you have I think 3 rows yang ada K. So you need to determine all possible range of K from each rows. Okay. So sini row S1 ada K. So kita kena cari range of K dia. And then row S0 pun ada K. So kita kena cari range of K to make sure that the first column is positive or no sign changes. Okay, any question? Any other question?
Yang saya cakap tadi kan yang table yang belah kiri tu. Table
Ni?
yang tadi tu. Yang tu table saya cakap right hand side.
Oh, itu determine stability. Ni kalau ada sign changes, maksudnya ada poles on right hand side. Poles tu apa? Study balik.
Okay sir.
Okay. So kena buat project. Project ada pasal poles. Okay, so I want to remind again, please do not forget to submit your project. Okay. Tak ada alasan kalam down. Okay, boleh hantar awal.
Sir, kan untuk part 2 dengan part 3 tu kan ada kena kira steady state error tu kan, kita tak belajar lagi.
Okay, yang tu awak boleh cari dari graph MATLAB. So,
Jadi guna MATLAB je lah.
Sebab yang tu tak ajar lagi, tak apa. Yang tu, yang steady state error tu tak ajar lagi, tak payah kira manual lah. Awak cari dari MATLAB maybe. Lagi cantik kalau dari graph tu awak tunjuk dekat mana value, contohnya peak time for example, settling time. Sebab dalam MATLAB boleh keluarkan values tu. So saya nampak ada orang yang dah submit, bukan section kita lah. Ya, ada orang yang dah submit, dia determine guna cara lain. Ada formula apa saya tak tahu dia pakai MATLAB. So yang dia pakai tu dia just keluarkan values je, tapi tak cantik lah. Dari graph tu tak nampak kat mana time tu. So lagi cantik kalau boleh dari graph tu tunjukkan dekat mana time tu. Macam pinpoint kan dia, keluarkan point dia. Rasanya link yang saya bagi tu ada ajar, tapi tak tahulah. Mungkin student yang hantar tu dia tak percaya kot dengan link tu. Okay, so macam steady state error tadi, cuba keluarkan value tu dari graph, dalam graph. Just indicate, okay?
Okay sir.
Okay, any more questions regarding project ke? Boleh tanya. Okay, sebenarnya kita punya syllabus ni dah laju juga sebenarnya. So, hari Rabu ni kita cancel kelas, okay? Kita jumpa lagi hari Isnin depan. Okay, so that's it for today's lecture. I hope you can understand. And if you don't understand anything, just let me know. Okay, so that's it. Assalamualaikum and goodbye.
Thank you, sir.
Thank you.
Thank you.
Thank you sir.
Thank you, sir.
Thank you sir.
Thank you, sir.
Thank you, sir.
Sir,
Hmm.
ada kat UMP ke?
Kenapa?
Itu sir.
Tak ingat nak tanya pasal projek depan.
Oh, saya tak ada dekat UMP Gambang.
Aduh, sir, kenapa tak pergi UMP abang?
Buat apa jauh?
Serius lah?
Betul, tak ada.
Aduh,
Tak pergi
Sebab
kot,
tak
maybe
tahu
tak tahulah bila nak pergi.
sebab kurang macam tu sikit lah. Macam, sebab ada, kalau ikut yang saja tu macam faham tapi tak tahu, tak apa. Sebab nak factorize ke, nak kena kembangkan ke,
Mana ada kan
yang part
negative
tu,
value je.
part tu kan pole kan. So sekarang ni kalau ikut nomometrik tu jadi macam dia tak sama yang atas dengan yang bawah.
Ya ke?
Tak apalah, nanti saya try buat dulu sekali lagi. Lepas tu pun saya hantar kat saya macam ni.
Awak salah soalan ni. Sekejap.
Lepas
Asal tak boleh, tak sama pula.
lepas saya try buat sekali lagi.
Part 2
Part 2. Part 1 dah settle lah.
Oh, part 2 Kan ada ajar itu tutorial.
Ada. Sebab tahu lah, saya punya tu macam nombor atas dia lain dengan nombor bawah So
Memanglah.
macam,
Memang lain. Memang akan lain. Tapi macam dalam tutorial hari tu ada ajar macam mana nak bagi dia sama.
ya sama ada tak macam saya buat tu se-factorize kan. Tahu saya factorize tak boleh.
Entah.
Sabar, try balik nanti. Try balik sekali.
Okay.
Thank you sir.
Okay.
Assalamualaikum.
Assalamualaikum.
Assalamualaikum.